All right, so we left off here on this slide talking about shell vacancies in atoms. When we're talking about shells, we're talking about the placement of electrons around the atom's nucleus. So we said that unfilled vacancies, remember, as you can see in here, you have, here's an atom, okay? And in the second most outer shell, it has 8 electrons. Okay, so this is a full orbital. So this would make it happy. All right, but here it has this extra electron. All right, to make it 11. Excuse me. And so this atom really wants to give this electron away. It wants to donate it. All right, because if it gets rid of this electron, then it gets rid of this orbital, and then it would have a complete outermost shell. All right, and then contrast that with this one, you have an atom with 17 electrons. And in the outermost shell, it just needs one more electron in order to complete that outer shell. And so it really wants to accept an electron. All right, so you see the difference here. And here, this atom wants to donate this electron so it can have a complete shell, outermost shell, and this atom wants to accept an electron, all right, and to complete its outermost shell. All right, and if this one is going to donate to get rid of this, it now only has 10 electrons and 11 protons still. So would that carry a charge? Yes, it would carry a positive charge. In this atom's case, if it receives that extra electron, it now has 18 electrons in the orbitals versus 17 protons in the nucleus. So would that carry a charge? Yes, it would carry an overall negative charge. All right, and that's what we get to here, free radicals and ions, and that's where we left off. All right, and so again, free radicals are unstable atoms or groups of atoms with unpaired electrons that can react readily with other atoms. All right, and ions are atoms that typically exist with an uneven number of protons and electrons and thus carry a charge. All right, so the way this atom usually exists, all right, and we'll talk about this, I'll just go ahead and mention it now. This is sodium. All right, and sodium usually exists as an ion because it usually exists with a positive charge. This one is chlorine. All right, and it usually exists as an ion because it accepted that extra electron, and so it usually exists as an ion with a negative charge. All right, and so if you have an atom that carries a positive charge, that's an ion, and it's specifically referred to as a cation. All right, those are positively charged ions. And then if you have an ion with a negative charge, all right, such as this one, that would be referred to as an anion, all right, which is a negatively charged ion. Now, free radicals you may have heard about when discussing health or nutrition, because free radicals can be harmful to the body. All right, and because they can be harmful to the body, we stress a lot of things. Hey, you need to eat things that are high in antioxidants, like grapes, okay, grape juice. A lot of people drink grape juice or wine for the antioxidants. Well, what's the purpose of the antioxidants? Well, the antioxidants will readily give up an electron to free radicals to make them less reactive, to make them more stable. All right, so atoms can solve the problem of unfilled vacancies by participating in chemical bonds. So a bond is formed when 2 or more atoms come together. All right, and so these chemical bonds are an attractive force that arises between 2 atoms when their electrons interact. And when you have 2 atoms come together, that makes a compound. So compounds are molecules of 2 or more different atoms. All right. And so when you have let's say two atoms are the same, come together, well, that makes a molecule. All right, well, let's say, what's table salt? Well, table salt is sodium chloride, NaCl. Well, those are two different atoms come together to form in a bond, and we'll talk about that in a second. Well, then they will form a compound. All right, and three types of bond we'll discuss: ionic, covalent, and then hydrogen. Okay, so chemical reactions can alter the bond. All right, so you have chemical reactions that can bring atoms or molecules together to form bonds, and then you can have chemical reactions that can break molecules or break compounds apart. All right, and so these chemical reactions are influenced by different factors such as temperature, concentration, and catalyst. And we'll talk about this later on in the semester, but go ahead and mention it now. All right, so ionic bonds. So ionic bonds are chemical bonds that exist due to a strong mutual attraction between ions of opposite charge. All right, so here, when you think of ionic bonds, you should think opposites attract, opposite charges attract. And so some classic examples of molecules or compounds that exist through ionic bonds are NaCl, we mentioned that, table salt, potassium chloride, and potassium iodide. Now they retain their respective charge. All right, so we said in that previous slide that sodium usually exists as a cation, a positively charged ion, and chlorine usually exists as an anion, a negatively charged ion. So even though they have this ionic bond, all right, they retain their respective charge. Okay, so even though they are bonded together, sodium will still be positively charged, and chlorine or chloride will still be negatively charged, even though they have this chemical attraction, this chemical bond, and because they retain their respective charge, it's said to be a polar molecule. All right, and so when you have polarity, it means that you have a separation of charge into positive and negative regions within the same molecule. So NaCl, all right, is a molecule. It's a compound. All right, they are attracted to one another. They are bonded together through these ionic bonds. But like we said, Na still stays positive, and Cl still stays negative. So they have polarity because you have a positively charged region and a negatively charged region within this compound. All right, and so that gets to the idea of electronegativity. So electronegativity measures the ability of an atom to pull electrons away from other atoms. All right, and so electronegativity depends on the atom size, how many vacancies it has, and what other atoms it is interacting with. All right, so in here, because in this compound, as we will go back, right? Because here, chloride is wanting to accept this electron. It wants to take this electron away from sodium, okay? And sodium's okay with that, all right? Because what they're both wanting are complete outer shells, all right? We would say that chlorine has a higher electronegativity than sodium. All right. Now you look at another atom that may have two vacancies, all right, in their outermost shell. They would be considered more electronegative because they're wanting to pull more electrons to their to complete their shells. All right. So here this is that same illustration. We're talking about sodium and chlorine. All right, sodium wants to give this electron up. Chlorine wants to accept it. And so because of this, they sort of have this connection through this electron, this red electron here. All right, and so that becomes this ionic bond, in that they retain their charge, okay? And so this would be considered a polar molecule because there's a positively charged region of the compound and a negatively charged region of the compound. Right, the next type of bond is covalent bonds. Here, there's a sharing of a pair or pairs of electrons. All right, and the covalent bonds form between atoms with a small or not a big difference in electronegativity. All right, and those covalent bonds are often stronger than the ionic bonds. All right, and they can exist as a single covalent bond if they're just sharing a pair of electrons. Okay. All right, so here you have 4 molecules of hydrogen. All right, and then you have a carbon molecule. Okay, and as you can see, all right, here, and showing their shell models. So carbon has an atomic number of 6. So there you have 6 electrons. Well, how many electrons does carbon need to complete its outer shell? Well, it needs 4. All right. So it will interact with 4 atoms of hydrogens. All right. Each one being a single covalent bond to form what we call methane. So methane has 4 single bonds between a carbon molecule and 4 hydrogen molecules. Okay, and they are sharing these electrons. All right, and what does that do? Hey, you see these electrons. All right, these 2 electrons complete hydrogen's outer shell. All right, and they also help complete the outer shell of carbon. All right, so you can have a single bond. You can also have a double bond. Well, they're sharing 2 pairs of electrons. All right, and as you can see, when a double bond is stronger than a single bond because 2 pairs of electrons hold the nuclei of the 2 atoms tighter and closer together. All right, so double bonds are harder to break apart than single bonds. Okay, well, what's stronger than a double bond? Well, that would be a triple bond. All right, and here a triple bond is sharing 6 electrons. So when 2 nitrogen molecules come together, all right, to form N2, they'll do that through a triple covalent bonding. All right, and triple bonds are harder to break than double bonds. All right, so covalent bonds in compounds are usually polar. Okay, all right, and so atoms share electrons unequally in a polar covalent bond, meaning that the electrons, even though they're being shared, they're really kind of being pulled closer to one than the other. All right, it's like the 2 atoms are kind of having a tug of war. All right, and the more polar or the more electronegative atom is sort of winning that tug of war. They're able to pull that electron closer to one another. I mean, closer to its side. All right, an example is a water molecule. All right, now you can also have covalent non-polar bonds. All right, now if they are shared, truly shared equally, then that would be considered a covalent non-polar bond. All right, so here let's just take a step back. So in the ionic bond, all right, one electron is really donated to the other atom. All right, such as sodium and chlorine. All right. Well, whereas in covalent bond, we say the electrons are shared with covalent bonding. But then under covalent bonding, you can have polar covalent bonds and non-polar covalent bonds. And if those shared electrons are pulled closer to one of the atoms than the other, then it would be a polar bond. But if they are shared equally with one another, such as in hydrogen gas, then it would be a nonpolar covalent bond. Okay, so we went over we went over ionic bonding, went over covalent bonding. Now let's go over the third one, and that's hydrogen bonds. Okay. All right, so the water, and when we talk about hydrogen bonding, we're going to focus on water because water has unique properties that arise from the two polar covalent bonds in each water molecule. Okay, so when we're looking at water, all right, and you may also know water is H2O. Okay, so you have an oxygen atom bonded with two hydrogen atoms. All right, and so in that H2O molecule, you have two polar covalent bonds. All right, and so those electrons, the oxygen is pulling those electrons from the hydrogen atoms closer to it. All right, and so it's a polar covalent bond. So in water, the oxygen atom carries a slight negative charge because they are able to pull those electrons closer to itself. So we carry a slight negative charge, and the hydrogen atoms carry a slight positive charge. Okay, so we say, so water is a polar molecule, and the polarity of individual water molecules attracts them to one another. All right, so you have the hydrogens of one molecule, of one water molecule, also being attracted to an oxygen atom of another water molecule. All right, and those types of interactions are called hydrogen bonds. Okay, so we want to make sure you keep it straight. So within a individual water molecule, all right, the O and the two H's are bonded through polar covalent bonds. But then you also have bonding between neighboring water molecules. Okay, and those attractions between neighboring water molecules are referred to as hydrogen bonds. All right, so hydrogen bonds are attractions between a covalently bonded hydrogen atom and another atom taking part in a separate polar covalent bond. All right, so hydrogen bonds can also happen in other molecules, but in this instance, when we're talking about water, the hydrogen bonding happens between hydrogens of one water molecule and the oxygens of other water molecules. Okay, so here are polar covalent bonds. Here are polar covalent bonds. Polar covalent bonds. Okay, so we're talking about within a water molecule, but we also have bonding between water molecules. So here we have a hydrogen bond because this guy in this water molecule is attracted to this oxygen in this water molecule. Same thing here. So these dashed lines represent hydrogen bonds, whereas the full lines represent polar covalent bonds. All right, and in these symbols here, that represents the polarity of the molecule. So again, we said the oxygen in a water molecule carries a slight negative charge, whereas the hydrogen molecules carry a slight positive charge. So hydrogen bonds, attraction between a positive hydrogen atom in a polar bond and a negative region of a nearby polar molecule, in this case oxygen in nearby other water molecules. And properties of water due to hydrogen bonding between water molecules. Okay, so those hydrogen bonding of water gives water certain properties, such as cohesion. Okay, cohesion refers to the attraction of water molecules for each other. All right, if you didn't have those hydrogen bondings, then water molecules wouldn't have that property of cohesion. All right, and that is the attraction between other water molecules. All right, water also has adhesion, and that is a property, and that refers to the attraction of water molecules to another substance. Okay, all right, So each bond is weak. Each hydrogen bond is weak, but a large number of hydrogen bonds make an overall effect important. So each single hydrogen bond is weak, but together it makes them strong. So if you have a bunch of hydrogen bonds, it will make it strong. Okay, hydrogen bonds can form and break much more easily than covalent or ionic bonds, but again, collectively they're quite strong. Those hydrogen bonds stabilize DNA and protein structures. Okay, so it's not only in water. We'll talk about hydrogen bonding when we talk about the structure of DNA. All right, and extensive hydrogen bonding among water molecules give liquid water several special properties that make life possible. All right, so let's talk about some of those properties of water that makes life possible because of the hydrogen. Because of the hydrogen bonds. Water heats up slowly and cools down slowly. All right, so it keeps living things at even temperature. That's why a large part of your body is made of water, or the importance of that. It helps keep your body at a sort of within a certain range. Okay, it helps do that. All right, in solid form, water is less dense than liquid. All right, so that's why ice floats. Otherwise, bodies of water would freeze solid. Water has a high heat of vaporization. That helps us when we're trying to lose body heat. So we lose a lot of heat energy when the sweat on our skin evaporates. Water molecules cling to each other and to substances such as glass that it can form bonds with. All right, and water is very polar. It surrounds polar solutes and charged ions, allowing them to dissolve in water, meaning that water is a great solvent. Okay? All right, what is a solvent? It's a substance that can dissolve other substances. Okay, so let's say, for instance, we talked about sodium chloride. Well, does salt dissolve in water? Yes, absolutely. Okay, you do it while you're cooking. We have seawater to show that salt dissolves in water. So water makes an excellent solvent, all right, dissolving polar molecules. All right, allows them to dissolve. So what do we call a substance that dissolves in a solvent such as water? We call that a solute. All right, so polar and charged molecules are hydrophilic, meaning water-loving. All right, they readily dissolve in water. Nonpolar molecules, which we'll talk about in the next lecture, are hydrophobic, meaning water-fearing. So these are important properties of water that affect so many parts of life. All right, and it has these properties in large part because of the hydrogen bonds. Now you can measure the amount of hydrogen ions in a solution, okay, and that is termed the pH of the solution. All right, so when you have a solute dissolved in a solvent, then you have what's called a solution. All right, and if you measure the amount of free hydrogen ions, okay, in that solution, then you're measuring the pH of that solution. What does that pH refer to? Basically, you're trying to measure the acidity of the solution. All right, and so when water splits, it splits into ions. Okay, and what it usually does, water, that H2O, will lose one of those hydrogens. All right, and so the hydrogen ion, all right, is an acid, and then the OH, hydroxide ion, is a base. And the greater the number of hydrogen ions in solution, all right, the lower the pH of the solution will be. The greater the number of hydroxide ions in solution, the higher the pH. Okay? All right, so again, it's important that you understand that relationship. The higher the pH of a solution, the more hydroxide, the higher the concentration of hydroxide ions, and thus the lower amount of hydrogen ions you have in solution. Okay, the lower the pH, all right, the greater number of hydrogen ions you have in solution, and the lower number of hydroxide ions in solution that you have. All right, and the lower the pH of the solution, the more acidic it is. The higher the pH of a solution, the more basic it is. And we can measure that using a pH scale. All right, so you have acids that readily donate hydrogen ions. And on that scale, okay, it goes from 1 to 14. All right, and 7 is neutral. Where do you think our body likes to be? Around 7 pH, pH 7, neutral. But the further you get away from 7 on the scale, the more acidic the solution is, and the more readily those acids donate hydrogen ions. Okay, the more hydrogen ions are in solution. All right, the further you get away from 7 to 14, the more basic or also alkaline that solution is. All right, and then the higher the hydroxide ions are in solution. Now, both acidic solutions and basic solutions can cause major damage. Okay, and again, so this pH scale, you're measuring the pH of a solution, and basically you're measuring the hydrogen ion concentration in that solution. Okay, and so the lower the pH, okay, or further lower you get from 7, you're increasing the amount of hydrogen ions in solution. Okay, if you go above 7 toward the basic end, you're increasing the hydroxide, the OH negative concentration, but you're lowering the lowering the hydrogen ion concentration. All right. Now, this is what's considered a log scale, meaning that if you go from pH 7 to pH 6, you're not going just this has one time fewer number of or one time more hydrogen ions in solution. That's 10 times more. So from pH 6 has 10 times more hydrogen ions in solution than something at pH 7. Okay, if you go to pH 5, all right, again, this is a logarithmic scale. Okay, so you're saying if you go at pH 5, that means a solution at pH 5 has 100 times more hydrogen ions than something at pH 7. All right, so here you see just some examples of things at different pHs. Okay, a lot of things that we eat. Okay, different soft drinks. That's why they say it's not good to drink a lot of soft drinks, because the acidity of the soft drink can ruin your teeth. All right, so again, it's at pH 5. All right, things that citrus fruits are very acidic. Okay, all right. But then you go up to the basic region of the pH scale, and again, things that we use, but things that can cause major damage. So it doesn't matter if you go to basic or acidic. Solutions at very high pH and very low pH can cause some major damage. All right. That doesn't mean you don't have these things in your body, because look here, you have very low pH solutions in your body, in your stomach. All right. But what happens when this stuff gets outside the stomach? You get some damage. All right. So your body has to maintain a normal pH range. Again, right around pH 7. All right. And so in this, the way they maintain that normal range is through this process called homeostasis. You'll cover this a lot more if you go into anatomy and physiology. Okay, but basically it's just this process of trying to keep your body within an acceptable range. In this case, pH of the body, all right, around 7. Now you can have shifts in pH quickly. All right, your blood pH can drop, and if that does, it can cause a coma. All right, so if you, for whatever reason, you get a lot more hydrogen ions in your blood, your blood pH is going to drop and can cause a coma. All right. You can have respiratory acidosis, meaning high carbon dioxide levels, okay, causing the pH drop in blood and muscles. You can also have respiratory alkalosis, meaning you have increase in blood pH. But your body usually has buffer systems to try to readjust the pH. All right. Now it's limited, so if your body goes way out of whack, these buffer systems may not be able to adjust, and you may have to have medical intervention in order to get your body back into normal range. All right, but here's the buffer system that your body employs in order to keep that normal pH range. So when the blood pH rises, all right, carbonic acid dissociates to form bicarbonate and hydrogen ions, okay? So if your blood pH rises, what happens? It's becoming more basic. Well, what do you need in order to lower that basic solution? You need hydrogen ions, okay? Well, there you go. All right. When the blood pH drops, what do you have more in solution? All right, you have more hydrogen ions. All right, so what does your body have to get rid of? It has to get rid of those hydrogen ions. All right, in this case, bicarbonate binds hydrogen ions to form carbonic acid. So in your blood, you have carbonic acid. All right, that's always there. All right, and so that carbonic acid can either disassociate or it can form in response to changes in your blood pH. Okay, all right, and so if your blood pH rises, become too basic, it can disassociate to increase the amount of hydrogen ions to lower your pH, all right, to normal range. Or if your pH drops below normal range, then bicarbonate can form, and thus sort of taking out those hydrogen ions out of solution to bring your blood pH back into normal range. All right, so that's the end of this lecture. Just some things that you really want to pay attention to. Again, this is not an exhaustive list of things. Okay, there could be things on the test that are not on this list, but if you know these things, then you'll have a good foundation from this lecture. So parts of the atom and characteristics, okay? So including subatomic particles. Okay, how are the atoms organized in the periodic table? What did we talk about? Atomic number, atomic mass. What are isotopes? Then we talked about electrons, the behavior of electrons. We talked about valence electrons. We talked about shell models. Make sure you understand how to construct a shell model. Then we talked about the different types of bonds and their characteristics. All right, we talked about the importance of water. And then we finished talking about pH scales, the differences between acids and bases. All right, so if you know these things, can discuss them, then you should have a good foundation from this lecture. But as always, if you don't understand anything, please ask questions so I can help you out.